Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler. Today we're going to be doing Unit number 7, Lesson number 5, Motion Day 1. This is one of my favorite parts of the course that we're heading into because we start to really apply our calculus. We use it in ways that I think that we can all kind of appreciate and understand the development of it a little bit better, and we'll be talking a little bit about the historical development of calculus as we talk about motion. But let's get right into the discussion. See, today it's all going to be about the story of a red dot and a green dot. Not really. Actually, today it's all going to be about one-dimensional motion. Okay, one-dimensional. So we're not talking about a football flying through the air and keeping track of its exact position. We're talking about keeping track of position in only one dimension. So either we're going to have movement that is completely horizontal, and we're going to keep track of its x-coordinate as a function of time, or we're going to be talking about purely vertical motion, and we're going to be keeping track of its y-coordinate over time. So just take a look at the picture on the left, right? We could just have a particle moving along the x-axis, and what we want to know is what x-coordinate is it at a particular time. Same thing with the y. Take a look at the right axis, that vertical one. Maybe we're keeping track of this green dot, or whatever it is, as time moves on, right? So keep that in mind, one-dimensional motion. Sometimes when we look at a graph in 2D, right, we're going to see x. The x-axis is actually time. And it very well could be that the y-axis is x, the horizontal position. So that can get a little bit confusing, obviously. Anyway, let's go on and do the first problem. Okay, in the first problem, we're gonna work through some of the math, and we're also going to introduce some concepts and some terminology. So keep track of the things that are in bold, okay? Let's take a look at what we have. The horizontal position of an object, so we're talking about horizontal position, x, is given as a function of time by the equation x of t equals t squared minus 8t minus 3, where x is in centimeters, pay attention to the units, and time is in seconds. All right. What is the initial position of the object at t equals 0? Include units, give an interpretation of your answer. Pause the video right now. You can figure out what x of 0 is, and then think about what it means. All right, let's take a look. Should be easy, right? Very simple calculation. X of 0, right? And we could go through all of the math, but 0 is such a nice number, especially when you're dealing with polynomials. We find that x of 0 equals -3, and include those units, centimeters. So what's the interpretation? It's really, really quite important. The interpretation is, as we keep track of this object moving along the x-axis, right, that it starts right here, right? So it starts at a position of -3, or it starts 3 units to the left of the origin. Right? And we want to keep that in mind. Right. It doesn't tell us anything about which direction it's moving in. It doesn't tell us anything about whether it's moving at all at t equals 0. All we know is that if we took a picture of this object right when we started our stopwatch, that's where it would be located. Make sure to really understand that. All right. The next problem asks us to determine the displacement of the object over the interval 0 to 10 seconds. Give appropriate units and an interpretation of your answer. So displacement, that's a new piece of terminology, but it's going to be very simple. The displacement is literally the change in position. All right, and we can actually use some nice mathematical symbolism for this. In this context, we'll call it delta x. Okay, it's the change in position. So in this particular case, the change in the horizontal position would be the position at 10 seconds minus the position at 0 seconds. Of course, what we would then have to do is actually calculate x of 10. I'm not going to go through that right now, but it ends up being 17. X of 0, as we already found, was -3. And so that we find a displacement of 20. Now keep in mind, this has units of centimeters, this has units of centimeters, so our displacement is going to have units of centimeters. Now the question becomes, what's the interpretation of that? What does that mean? Pause the video and think about that for a minute. All right, what a displacement of 20 centimeters means is that the position has increased by 20 centimeters. Or if you really wanted to make a nice interpretation, we end up 20 centimeters to the right of where we began. Or maybe we should talk about the object. Maybe it's not us that's actually traveling, right? But really, the position increased by 20 centimeters. That's the key here. All right? Now, letter A, that's a static thing, right? Where are we at t equals 0? Letter B, here we're measuring change. How much has the position changed? And I want you to keep in mind, of course, that the displacement can certainly be negative. If we had a negative displacement, it would just simply mean that our position overall decreased. Okay? I'm going to clear out this text and continue on with this problem. Okay? Now, letter C says, well, let's find the average rate of change of the position, which is known as the average velocity. So this is actually a piece of terminology that I expect my students to know, the average velocity, which is just an average rate of change. So you've been doing average rate of change for a while now, right? Average velocity is just the change in position divided by the change in time. So in this particular case, we would have the position at 4 centimeters minus the position at 0 centimeters, all divided by 4 minus 0, right? So really, what we have is displacement divided by elapsed time, right? That's what we have. Displacement divided by elapsed time. So again, we could kind of go through all of this, but x of 4 is negative 19. X of 0, as we found out, was negative 3. Got to be very careful of this subtraction. Divided by 4. That's going to give us negative 16 divided by 4, and that's going to be negative 4. Now let's talk about units, right? Again, the units of the displacement were centimeters. The units of elapsed time will be seconds, so we have negative 4 centimeters per second, right? And we're very comfortable with rate units at this point. Let's do the average velocity from 0 to 10. Why don't you pause the video right now and do that calculation? All right. Let's take a look at it. So in this case, right, delta x divided by delta t is going to be the position at 10 minus the position at 0 divided by 10 minus 0. The position at, well, the position at 10 ends up being 17, right? We already knew that. The position at 0 was negative 3. So this was actually the calculation that we did in part B, right? Right, when we asked what the displacement was from 0 to 10. In fact, we could have used that answer immediately. I'm not sure I can edit that out. So we'll get 2 centimeters per second as the average velocity on the interval 0 to 10 seconds. So this is kind of neat, right? I'm sure you've been around long enough and you've seen enough modeling problems that you're probably comfortable with units of velocity. Miles per hour, feet per minute, centimeters per second, right? Here, again, what we're looking at is this average velocity. So in other words, if, I know that I've got an elapsed time, 4 seconds in letter I or whatever, 10 seconds in letter I, and I know my displacement, I can calculate an average velocity. Now what's fascinating is this is where Newton was really going. Newton understood average velocity, every physicist of his day did. But what he really wanted to quantify was how fast the position of an object was changing at a moment in time. And quite frankly, he was belittled by this, and for good reason, right? Everything physicists thought about at the time in terms of motion was motion over elapsed time. So how much has the position changed over elapsed time? Well, that's average velocity. How much did the velocity change over elapsed time? That's average acceleration. So there was always a change in time, but Newton wanted to say, no, I want to quantify the velocity in an instant. And that's where instantaneous velocity came in. Now, I hope that this doesn't, confuse you too much, but I'm going to actually draw just a little sketch of x versus t, okay? Now this is a sketch that kind of looks something like this. If we just do our, let's say, our 10-second interval. And what we've been doing in the last problem, right, let me do a different color. What we've been doing in the last problem, let's say, is we've been finding slopes of secant lines. So let's say that this was our 4 seconds, right? And this was our position over here at -19. Right, what we've been doing, oh my goodness, that was just terrible. I'm not sure I can even get rid of it now. Train wreck. All right. And for some reason, I'm gonna take another shot at it. Oh, it was just worse. Anyway, we've been finding the slope of this secant line. I have to work on my drawing. We've been finding the slope of this secant line. But now we're being asked to find the instantaneous velocity at 1 second, right? And what is that going to be? What's that going to be? Pause the video right now and think about it. What thing do we know that will now allow us to find how fast something is changing at a point? Figure it out. It is the derivative. We'll put it in green because it's going to allow us to go, right? So the derivative, right? I don't have to talk about elapsed time anymore. I just have to talk about why I can't draw a tangent line, right? This slope, the slope of that tangent, that's going to be the instantaneous velocity. Okay, so we're just going to call that v of t, right? And we're going to say v of t is the derivative of the position. All right, that's very simple here, right? 2t minus 8. If I want now the velocity at 1, it's simple enough to just substitute in. And I get -6. The units are the same units because we're still just doing the change in position over the change in time. But just remember, what we just found was that if we've got a position formula, the displacement divided by the elapsed time, that gives us average velocity. But when we want to know how fast something is moving and in what direction, right? So that's something that we hadn't pointed out before the commercial break, is that because v of 1 is negative, the object is moving to the left, right? And that's something that students can really lose in terms of understanding while they're going through the motion work. All right, so take a look at everything. Pause the video if you need to, because I'm going to scrub the text. Okay, here it goes. All right, so our motion summary so far. Okay, eye on the ball. We're going to keep track of just the x-coordinate or just the y-coordinate of an object. That's it, just x, just y. All right, if we find the change in x or the change in y, which can be positive or negative, that's just the displacement. It's not how fast it happened. Just, oh, hey, my x-coordinate increased by 10 units. My y-coordinate decreased by 3 units, right? When we divide that displacement by some elapsed amount of time, so, hey, I moved to the right 6 units over 2 seconds, right? Then I went, on average, 3 centimeters per second, right? But if I want to know how fast I'm moving at a moment in time and whether my position is increasing or decreasing, then I need my derivative. Now, we're just going to call that velocity. Technically, it's instantaneous velocity, but we'll know the difference between average velocity and velocity by using the word average. Okay? So let's apply this now in a problem, and we're going to use our calculator for this, all right? So get those calculators out, get them ready to go. It says weight is attached to a spring such that its vertical position, so we're talking vertical motion here, in inches above the ground is given by this function. All right, so I really want you to understand, all we're getting as an output is the inches that this object is above the ground, and the input is the number of seconds since the spring was released. All right? Now, I'd like you to use your technology on this as much as possible. I would even use the function option in your calculator, and I'll bring out the calculator to show you how to do that in a second, but it really makes this nice. Letter A says find the average velocity of the mass over the interval 1 to 6 seconds, include appropriate units. So what we're going to want is delta y divided by delta t, right? So the y-coordinate at 6 minus the y-coordinate 1 divided by 6 minus 1. What I'd like you to do is work out that calculation. All right? All right, let's take a look at a great way to do it on the calculator, and this is going to set us up nicely for letter B. So I'm going to open up the calculator. All right, let's go into y equals. Now, I know that the input here is going to be x. We have to be flexible enough in our thinking to realize that x in this formula stands for time. So I'm going to enter my formula, 42 minus 6 times e to the negative, make sure you use a negative, t divided by 5. Okay, put in my cosine, pi divided by 2 times t. Parentheses, enter. Okay, check my function out. It looks good. Let's go out to the main screen. Now I'm not graphing this. Okay, what I'm going to do is use that function notation on our calculators to actually evaluate the displacement, and then I'll divide it by the elapsed time. So I'm going to go into vars, go over to yvars, immediately grab onto function, and grab onto y1. Okay, I'm back out of the main screen, so I'll put in y1 of 6 minus, go back in, y1 of 1, okay, and now enter. Now, what's cool is I can now just simply put in divided by 5, enter. And what I'm going to get is 0.361 here, right? This had units of what? Inches? Right here, units of seconds. So my average velocity was 0.31 or 361 inches per second. Isn't that function notation nice on the graphing calculator? I absolutely love it. Now we're going to use it as well in letter B. Is the object moving up or down at t equals 3 seconds? Justify. Now let me just be very clear what you can never do in a question like this. You can't say, well, I'm going to calculate the position at t equals 2 and t equals 3 and just compare them. All right? That would be basically saying, on the whole, between 2 and 3, did the object move up or down? I want to know, right at that moment, is the object on its way up or is the object on its way down? And what we're really asking in this question is y increasing or decreasing? And the way you always tell whether a function is increasing or decreasing is by using its derivative, right? That's how you tell, right? If the derivative is positive of anything, then that thing is increasing. And if the derivative is negative, that quantity is decreasing. So we use the velocity to determine whether the position is increasing or decreasing, going up, going down, going to the right, going to the left. I want you to use the numerical derivative on your calculator and try to use the function notation as well. All right, pause the video now. All right, let's do it. I'm going to bring the calculator up one more time. Hello, calculator. All right, I'm going to go out to the main screen. Okay, maybe clear it. All right, I'm going to go to Math, option 8, grab myself my numerical derivative, back out on the main screen, where it asks me to fill in the function, whether I'm using the old OS or the new one, like what I have here. I'm going to go to vars, yvars. I'm going to grab onto y1, back out to the main screen, and now I'm going to put in t equals 3, and I'm going to get the following. dy dt is negative 5.172. I have to put in the units, but those are going to be, again, in inches per second, and therefore the object is moving down because dy dt is less than 0. Explanation needed. Isn't that great, though? So velocity is going to tell us two things. It's going to tell us how fast and in what direction. So for those of you that like physics, of course, that means that velocity is a vector, right? Velocity is a vector. My contention is all slopes are vectors, right? Because slope measures steepness, but it also measures direction. So it has those two things, those two attributes going for it. I'm going to clear out the text, so copy anything down you need to. All right, let's do one final problem. An object moves along the x-axis such that its position is given by x equals 2t squared minus 9t plus 4, with the position in centimeters and the time in seconds. So we're not going to use the calculator on this. Letter A, what is the velocity of this object at t equals 1 second? Include units. Pause the video now and see if you can come up with that. Okay, let's take a look. Velocity, by definition now, is going to be the derivative of position. So I'm going to just state that immediately. V of t is going to be x prime of t. Real simple polynomial example, that's going to be 4t minus 9. So v of 1 is going to be 4 minus 9, negative 5. I need my units, right? This is the change in position divided by the change in time for infinitesimal. Centimeters, seconds, so centimeters per second. All right. Is the object moving to the right or the left at t equals 1 second? Justify. Pause the video again. Real simple, right? The object's moving to the left. Why? Because v of 1 is less than 0. Or because x prime of 1 is less than 0. All right. Letter C. When does the object temporarily come to a stop? All right. So, you got an object moving along the x-axis, and every once in a while it comes to a stop, right? Maybe sometimes it even does this, right? So, think about how you can find that moment in time. There's only one, so pause the video and think about it. All right, did you figure out 2 1/4 seconds? Hopefully, right? An object will always come to a stop when its velocity is equal to 0. Right? So that would be 4t minus 9 equals 0. T equals 9/4, and I think this is actually easier to think about in decimal form. So 2.25 seconds. Now, letter D says, does the object change direction at the point in time you found in part C, and how can you tell? This is a really, really important problem. All right? It's going to be the last one that we're going to do, but I really want you to understand. A lot of people assume that when the question is, when does the object change direction, all they have to do is figure out when it stopped. But I really want to point out an important distinction. An object can be moving, come to a stop, and then continue to move in the same direction, or an object can move along, come to a stop, and change direction. So don't always assume that when an object stops, it also changes direction. All right? Think about letter B. All right, pause the video and see if you can come up with a good explanation in D. All right, let's take a look. In order to justify that an object changes direction, all right, you must equate that to a change in the sign of the velocity. See, the velocity is what controls the direction, okay? So what we're going to do is something that looks and probably feels very familiar. I'm going to draw a velocity number line, and I'm going to mark on 2.25 seconds, and then I'm going to test something out here, like t equals 0. What am I going to test it in? I'm going to test it in the velocity formula, right? I'm going to test it in this thing, right? So v of 0 is negative 9, so the velocity is negative, which means we're moving to the left in here, right? Then maybe I take something out here like t equals 3. Velocity at 3 is going to be 12 minus 9, or 3, so it's positive, which means I'm moving to the right. All right, and so therefore I've changed directions because v of t has changed sign. All right, really critical. All right, I can't tell you how many times you may miss a problem that just gives you the position or even gives you the velocity, and says, when does the object change direction? You set that velocity equal to 0, you find all of the answers typically by factoring, and then you say, well, there they are. But the problem is, if the velocity doesn't change sign, the object doesn't change direction. All right, so always be adamant about checking that. Okay, I'm going to scrub out the text, write anything down you need to. There we go. All right. Well, I've been recording a lot of videos this week and getting a lot done. It happens to be January Regents Week in New York State. So thank you for joining me for our first day on motion. We're going to be doing more days on one-dimensional motion and eventually getting into vectors and two-dimensional motion. That's some of my favorite portions and some of my favorite topics in this course. Until next time, I'm Kirk Weiler. Keep thinking and keep solving problems.